Welcome to Edupedia World Grade 10 Computer Science Video Lecture Series. I'm Upeka Vandibona, and from this episode we are going to try out few questions regarding to propositional logic. Now before moving on, let me mention you few things again that we discussed basically in the previous episode. So here what we are talking about is propositions. Now from these questions what we are trying to do is, using the primitive propositions, we are trying to build up composite propositions, or else we can say compound propositions. A proposition is said to be primitive if it cannot be broken down into simple propositions. Otherwise, the proposition is said to be composite or compound proposition. This means that a composite proposition can always be broken down into a collection of primitive propositions. Now the most important thing in here is how we represent these compound propositions using notations. So in these questions we are learning about that kind of stuff, representing the compound propositions using notations. Now in here, before starting the questions, I want to give you this little tip over here about the words but and. When you are given a compound statement and if it includes the word but or and, remember we are using the same notations to represent both of them. And now with that, let's start the questions. In this question we are given three primitive propositional statements, and each statement is represented by a prepositional variable. The variable P represents I can sing, the variable Q represents I can dance, and the variable R represents I can play. And also we have given few compound statements that have built up using those primitive statements. Now what we have to do is represent these compound statements using the prepositional logic notations. Now let's take the first one, I can sing and dance. In this statement we uses the conjunction word and to connect those two primitive statements, I can sing, I can dance. If you can remember, we uses the turned V symbol to represent the conjunction operation. So this is how we can represent this first statement, P turned V Q. The second statement, I can sing but cannot dance. So in here it uses the negation of the primitive statement I can dance. Therefore when we are writing the variable Q, we have to use the negation of the Q. And also to connect these two primitive statements in this statement, it uses the conjunction word but. If you can remember, in the previous slide I mentioned both the words and for the word but uses the same notation, turned V. Therefore when we are representing this statement, we write it like this, P turned V tilde Q. The third statement, I can dance or play or can do both. A little bit tough one. Therefore let's try to divide this into two parts like this. In the first part, I can dance or play, here we are using the disjunction word or to connect those two primitive statements, I can dance, I can play. Now this is how we are going to represent the first part, Q, V, R. To represent the disjunction operation, we uses the symbol V. So to connect the first part and the second part, again we are using the disjunction word O. So again we have the symbol V in here. Now the second part, can do both. It means it can do both the things, I can dance and I can play. So here it uses the conjunction word and. So the second part is represented like Q turned V R. So these are the two parts connected with the disjunction word O. Now this expression is a little bit longer one. If we can reduce this expression, that is better. So if we apply the fundamental laws that we have learned in a previous episode, then we can reduce this expression. So let's first apply the distributive law for this. So if we apply the distributive law, we can reduce it into like this. And then here you can see it uses the same variable twice. If we apply the idempotency law for this, then we can reduce it like this. So again we have the same variable set repeated. So again, if we apply the idempotency law in here, at the end we will obtain a result something like this. So this is how we can represent this third statement in more reduced way. The fourth statement, I cannot sing and cannot dance. In here it uses negation of two primitive statements, and those two primitive negation statements are connected with the conjunction word and. So this is how we are going to represent it. Tilde P, turn V and tilde Q. The fifth statement, I can neither dance nor play. Here it uses totally different word sets to combine the two primitive statements, I can dance and I can play. But if you look more carefully, you can see the words not or, in other words no. So this is how we can represent it. Q, V, R and the negation of the whole of this. Now the last statement, only if I can sing, I can dance. Here it uses the IFF expression. In other words, biconditional expression. So if you can remember, the notation have the double-sided arrows. So we can represent it like this. P, double-sided arrow, Q. The next question, I cannot play. It is the negation of the primitive statement I can play. So the answer is tilde R. The next question, I cannot sing but can dance. So here it uses the conjunction word but to connect the primitive statement I can dance and the negation primitive statement of I can sing. So here we are going to represent it like tilde P, turned V, Q. Now the last statement, I can either sing or dance but cannot do both. Again a little bit tough one. Therefore let's try to divide this into two parts. The first part is I can either sing or dance. The second part is but cannot do both. So let's try to represent the first part, I can either sing or dance. Here it uses the disjunction word or, so we can represent the first part like P, V, Q. The first part and the second part is connected with the conjunction word but. So we can add the turned V after the first part. Now in the second part it says cannot do both. That means both the things I can sing and I can dance cannot be done. Therefore we can represent the second part as P turned V, Q and the negation of the whole second part. Now this expression is a little bit longer one. So if we apply the fundamental laws, we can reduce it into a more simplest one. The first law we can apply is the De Morgan's theorem. So after that we can obtain an expression like this, and for this expression if we apply the distributive law, we will obtain an expression like this. Now in here you can see it uses the negation of the other variable. That means we can apply the complement law. So with that the result would be 0 for those components, and with that we will obtain a final output like this. Now here is another question set. Here we are given two primitive statements, it is hot and it is sunny, and each of the statement is represented by the propositional variables P and Q. Now the first question says it is not hot but it is sunny. So we have to represent this statement, compound statement, using the prepositional logic notations. Now this statement uses the conjunction word but to connect the primitive statement it is sunny and the negation of the primitive statement it is hot. So we can represent it like tilde P turned V, Q. The second statement, it is not both hot and sunny. We first represent the hot and sunny by P turned V and Q, and then represent not both. So for the whole it is negation. The third one, it is neither hot nor sunny. So like as the previous, if you look more carefully, it have the words not or. That means first we have to represent the or functionality, P, V, Q, and the negation of the vowel. Okay, now here is another type of question. Here we have to show these two expressions are equivalent. So for that, we have to draw the truth table and show the final outputs for these two expressions are same. Now let's try to do that. First we need to identify what are the columns. So the first three columns are the initial inputs P, Q and R. And now for the rows, here we need 2 to the power of 3 number of rows. That means 8 number of rows we have in this truth table. The first half are zeros, the first 4 rows are zeros, and the second half of the rows are ones. And for the second column, first 2 rows are zeros and the second 2 rows are ones. And same goes with the second half. And for the third row, 0, 1, 0, 1, 0, 1 and 0, 1. Now let's take the left hand side expression. So this is the left hand side expression. So this is our left hand side column, and here this expression have the AND operation. That means whenever the input P is 0, the whole expression becomes 0. So this first 4 rows are anyway zeros because the input here is always 0. And for the next 4 rows, if we look at this part of this expression, Q or R. So whenever the inputs Q and R have the value 1, it gives the output 1. So if we take this row, 0 or 0 is 0 and 1 and 0 is 0. But for this row, 0 or 1 is 1 and 1 and 1 is 1. Therefore this row is 1, and same goes with the other 2 rows. 1 or 0 is 1. So the whole statement goes 1, and same goes with this row. So this is the final output of the left hand side expression. Let's go for the right hand side. Now for this right hand side expression, this is the right hand side column. Now in this expression, it combines 2 parts with a OR operation, and each of the part have the AND operation. Now if you look more carefully, you can see both of the parts have the input variable P. Whenever this input variable P have the value 0, that means both of the parts will gives you the output 0, and the whole expression goes 0. Therefore these 4 rows anyway get the value 0 because the input P have the value 0. And for the next 4 rows, if we consider P and Q, so if we take these 2 rows, the Q is 0, that means this part will become 0. And if we consider P and R, that means when the R becomes 0, the whole part becomes 0. So if we take this row, P and Q is 0 as well as P and R. Therefore the whole expression is 0. And if we take the next row, P and Q is 0 but P and 1 is 1. Therefore the whole expression becomes 1. And here P and Q is 1, therefore the whole expression becomes 1 because this part becomes 1, the whole expression becomes 1. And for the next row, here P and Q is 1, so the whole expression becomes 1. So you can see both the left hand side column and the right hand side column have the same output. That means these two expressions are same. Let's try to do another exercise on proving the equivalency of two expressions. So in here, the left hand side, it has P and Q and the negation of the vowel, and in the right hand side, negation of the P or negation of the Q. Let's try to prove these two expressions are equivalent. So for the truth table, the two inputs are P and Q, and there are 4 rows in this table. The first 2 rows are zeros in the first column, and the second half of the rows are ones. And now in here, 0 1 0 1. And now for the left hand side, this is the left hand side of the expression. Now in here, P and Q and the negation of the vowel. So in here, in the truth table, 0 and 0 is 0 and the negation is 1. 0 and 1 is 0 and the negation is 1. 1 and 0 is 0 and the negation is 1. 1 and 1 is 1 and the negation is 0. Now for the right hand side. This is the right hand side expression. Now in here we have negation P. That means 1 1 0 0. So this is the negation P, and we have the negation Q. So this is the negation Q, 1 0 1 0. And here the operation is O operation. 1 O 1 is 1. 1 O 0 is 1. 0 O 1 is 1. 0 O 0 is 0. So you can see two outputs are same in here. Therefore, the two expressions are equivalent. And with that, we are going to end up this session. So in this session, we try out few questions regarding propositional logic. In here, we learned how to represent compound statements using propositional logic notations, and also we learned how to prove the equivalency of two propositional logic expressions using truth tables. So that's what we brought here in this episode, and with that we are also going to end up the first section of our course, the computer logic. From the next episode we are going to start our second section, data representation section. So stay tuned on with Edupedia World, and thank you for watching.